Hello everyone, this is part 2 of lecture 10 in ComSci 123, Binary Search Trees. In the part 1 video, we introduced the concept of binary search trees. So they are binary trees that follows the BST order property, and that is the keys in the left subtree should be less than the key in the node, whereas the keys in the right subtree should be greater than the key in the node. Okay. We also introduced the concept of rotations like left rotate, right rotate, left right rotate, and right left rotate. And we do these rotations to restructure the tree, the BST, while keeping the BST order property. Okay. We also introduced the first balanced search tree, which was the splay trees. And the idea for splay trees is that each time you search, insert, or delete, you will splay that node all the way up to the root. Okay, and the reason for this is so that the next time that you do another operation on that key, then it would be faster because the node is already at the root or at least near the root. Okay, so that was the idea behind splay trees. Now in part 2, we will discuss more balanced search trees, right? So the reason for this is because binary search trees are good for searching, insertion, deletion. It will run in O of log n, but that is if the binary search tree has a height of log n, right? If it's balanced. But if it's very unbalanced, it's O of n. So that's why we are aiming to have balanced search trees so that at least our running time would be in O of log n, right? So the three balanced search trees that we'll discuss here would be the AVL trees, the red-black trees, and the 2-4 trees. Okay? So let's start with the AVL trees. So what are AVL trees? So AVL trees were created in 1962 by Georgi Adelson-Velsky and Eugenie Landis. So the AVL actually comes from their last names, right? So the last names of the creators, which is Adelson-Velsky and Landis. Okay, so what are AVL trees? So they are just binary search trees that follow the height balance property. Okay, so what is this height balance property? In a nutshell, it tells you that the height of the node's children can differ by at most 1. Okay, so before we go on further with height balance, let's try to define first what is the height of a node. Okay, so the base case or the most basic one would be the height of the null node. Okay, and that would be 0. So if you recall, null nodes are those nodes that have no items in them, so they are just there added as children of a leaf node, for example. So yeah, the height of a null node is 0. Next, if you have a node, it could have a left child and a right child, so let's call that LC and RC to make it shorter. So the height of a node would be whatever is the bigger height between the left child and the right child. So you take the max out of that and then you add 1. Okay, so let's say that the left child has a height of 3 but the right child has a height of only 1. So the bigger height would be 3, right? And then you add 1 to that, so the height of the node would be 4. Okay, so this is how you compute the height of the node. Now the node itself actually does not have a height. It's the tree that has height. So when you talk about the height of the node, you're actually referring to the height of the subtree rooted at the node. Okay, so it's a more technical way of looking at things, but to keep things simpler, we'll just call it the height of the node. Okay, so even if it actually means the height of the subtree rooted at the node. Okay, so let's see an example of how you compute the height of the node. So given this example here, let's try to figure out the height of the node. So the null nodes here would all have height of 0, right? So they'll all have height of 0. And then let's try the leaf nodes. So for here, they're both 0, so the max is 0, and then plus 1, so that's 1. Here it's also 1. Here it's also 1. Here it's also 1. But here for 48, you have left child is 0, right child is 1, so the max of that is 1, and then you add plus 1, so that's 2. The height of it is 2. Okay, and then for 17, the max is 1 versus 1, so it's still 1, and then plus 1, that would be 2. For 56, the height of the children are 2 and 1, so the max is 2 plus 1, you have 3. And finally, for 44, the max child height is 3 because you have 3 versus 2. So 3 plus 1 is 4. So the height of 44 is also 4. Okay? So for example, for 44, you have 1, 2, 3, 4, all the way up to the null node. So that is the height of the nodes. Okay? So I hope that concept is clear. So you have the height of the nodes here. So yeah. Now, going back to the height balance property, we'll define something called the node balance factor. Okay, so the balance factor, or BF for short, would be computed as follows. So the height of the right child minus the height of the left child. So you'll just take the difference of the height of the children. Okay, so based on the balance factor, we call the node left heavy if the balance factor is less than or equal to -1. So if the balance factor is negative, that means that the height of the left child is bigger, right? Because this equation became negative, so left child must be a greater number. So if left child is a greater number, that means that it's leaning towards the left, right? The height of the left child is greater, so you are left heavy. The opposite of that is it's right heavy if the balance factor is greater than or equal to 1. So if this value here is greater, then this whole equation would be a positive value, right? So for example, 5 minus 4, so 5 is the right child, so that would be a positive value, right? So an example here is, let's say you have 3 here and then 4 here. So if it's 4 minus 3, this is 1, so it's positive, so this one is right heavy, right? Because the right child is heavier. But what if it was 5 and 2? So 2 minus 5 is -3. So this one is actually left heavy because the left child is has a higher height or has bigger height. Okay, so that is what we mean when we say left heavy and right heavy. Okay, and then if the balance factor is 0, that means that they are of equal height. Okay, so when we talk about the balance factor of the whole tree, we are talking about the balance factor of the root node. Okay, so yeah, so if we ask is the tree left heavy or right heavy, then we'll just look at the root. So is it left heavy or right heavy or equal height? Okay, so that's the concept of balance factor. So right minus left, so that if it's positive, you have the right heavy, and then if it's negative, you have left heavy. Okay, so it might be useful to think of the numbers on a line, right? So if it's positive numbers, it's right heavy. If it's negative numbers, you have left heavy. Okay, now in some sources, you might see balance factor as left minus right, and then it's more or less the same, but it's you just flip the conditions here, so it would be the opposite. But for the sake of so that we can use this imagery here, that if it's left heavy, it's negative, right? And then if it's right heavy, it's positive. So we'll just use this equation, right minus left. Okay, so that is the node balance factor. So for AVL trees, we say that a node is balanced if the balance factor is in one of these three values. If it's -1, 0, or 1. So the absolute value of the balance factor should be less than or equal to 1. Okay, so it could be left heavy but only has a balance factor of 1. It could be right heavy but also a balance factor of 1, or it could be equal. So nodes that have this balance factor are called balanced nodes. Okay, so a BST is called an AVL tree if all nodes are balanced nodes. So that means that all of them have this as the balance factor. Okay, so the height balance property tells you, or because of the height balance property, this will assure that the tree's height, or the AVL tree's height, is O of log n, because you're more or less balanced in all levels, right? So you will have an O of log n height, which is what we want, so that the tree is, even if it's not fully balanced, it's mostly balanced, right? And so if it's mostly balanced, then your height would be O of log n, and so all of your operations, your search, your insert, and your deletion will also run in O of log n. Okay, so yeah, that's AVL trees. So let's see an example of this one. So in here we have 8 nodes, right? 1, 2, 3, 4, 5, 6, 7, 8. And the height of this is 4, right? So how did we compute 4? So log of 8 base 2, that is 3, and then plus 1, so that's why you get 4. So log of n plus 1 is just O of log n. So you see the height of the tree is in O of log n. Okay? Now, given these 3 heights, can we compute the balance factor of each node? Okay? So for null nodes, we won't compute those anymore since they don't have children anyway. So we'll just compute for the nodes with keys. Okay? So for this one, this is 0 minus 0. So this is balanced. This is also balanced here. This is also balanced here. This is also balanced. So if you have null nodes as children, your balance factor will be 0, right? Because there are no other nodes. For 48, however, you have a height of 1 and a height of 0. So that would be 1 minus 0. So the balance factor of this is 1. So this is right heavy because you have more nodes to the right. So you know that by the sign of the balance factor, which is positive. Okay. How about for 56? So you have 1 in the right child minus 2. So 1 minus 2 is negative 1. So the balance factor of 56 is negative 1. And you see that it's left heavy because it has more nodes on the left than on the right. Okay? So yeah, it's negative 1. How about for 17? For 17, you have 1 minus 1. So this is 0. So this is actually balanced because you have a balanced left and right subtree. Okay? And finally, for 44, you have the height of 3 for 56 and height of 2. So this is 3 minus 2 is 1. So everything is the whole tree is actually right heavy because you have a taller right subtree than compared to the left subtree. Okay, so those are the balance factors. So you have the zeros for those with null nodes as children, and then for 17 it's also 0, right? Because 5 and 32 are balanced, and then for the rest you have right heavy for 48, left heavy for 56, and then for 44 it's also right heavy. But you'll notice that all of them have a balance factor of 0, 1, or negative 1. So since it follows that property, then this tree is an AVL tree. Okay, so that is what we mean when we say it has a height. It follows the height balance property. So all nodes are mostly balanced. Okay, so even if it's not fully balanced, like balance factor of 0, the maximum that you could have an imbalance is 1. So it could be 1 that's leaning towards the left or 1 that's leaning towards the right, but at least you keep it at most 1. Okay, so that is AVL trees. So let's take a look at the operations that you can do on AVL trees. So for search, it actually it's very similar. It's the same thing as a normal BST search. So you just follow the normal search procedure for BSTs. But for insert and delete, we'll also start by doing the normal BST insert and delete. However, insertion and deletion are actually update operations, right? So for insertion, you add more nodes. For deletion, you remove nodes, right? So this might affect the height balance property. And for AVL tree, it must always enforce this height balance property. So whenever we insert and delete, we should check if any nodes violate the height balance property, and if there is an imbalance, we will fix that imbalance by doing rotations. Okay, so again, the concept of rotations is very helpful because in almost all balanced search trees you'll use the concept of rotations. Okay, so it's important that you really understand how to do rotations and how to recognize the pattern and the appropriate rotation that you need to do based on the pattern. Okay, so we'll fix those imbalance, and because of that, the AVL tree is a self-balancing tree because it does the balancing by itself after doing insertion or deletion. Okay, so it's a self-balancing tree. Okay, so for the update operations, which is insert and deletion, this is what we do after we do the normal insert and delete. So we'll check the ancestors, so that would be the parent, the grandparent, the great-grandparent, all the way up to the root of the inserted or deleted node for height balance violations. Now, we only need to check the ancestors because these are the only nodes that will be affected. The other parts of the tree won't be affected because they're not in your they're not related to the node that you just inserted anyway. So we'll see this in an example later, but you basically just have to check the ancestors, not the whole set of nodes in the tree. Okay, so check the ancestors for any violation. So again, it's a violation if the balance factor is not one of these three values, -1, 0, or 1. And if you find the violation, you'll restructure using a rotation. Okay, and the rotations here should be somewhat familiar to you already if you've watched part 1. So how will we do the restructuring? So it's based on the pattern again. So here we'll have a left heavy violation, and the violating node is called V. Okay, so the V node is the violating node, so it's violating the height balance property, so it's not -1 or 0 or 1, so maybe it's -2, right? So it's -2, so it's left heavy, so we look at the left child. Now if the left child is balanced, like it has a 0 balance factor, or it's also -1, so it's double left here, so left heavy right here. So if it's balanced or also left heavy, then we'll just do a single rotation to the right. So we'll rotate the left child to the right to make it balanced like this. Okay, so if it's balanced, you'll just rotate left child here, and then we'll get this one. So the left child became the parent, the violating node became the child. Okay, and then if it's left heavy also, so it has the same direction, then we also do a single right rotation to counter the left imbalance, right? So left child became the parent, and then the violating node became the right child, and then the grandchild of the violating node is still the left child of the L node right here. Okay, so based on this pattern, we'll do a right rotation. Now, how about if it's not it's also left heavy, right? So it's -2 still, the violating node is still has a balance factor of -2, but the left child is right heavy. Okay, so it's -2, and then the balance factor of the left child is 1, so it's right heavy. So if that is the case, we'll do a double rotation, a left-right rotation. So we'll rotate the grandchild to the left first. Okay, so by doing this left rotation, we come up with this, and then we do a right rotation on the grandchild to give you this final form. Okay, so you'll do a double rotate of the grandchild so that it becomes the parent of everything, and then left child is still the left child, the violating node becomes the right child. Okay, so this should be familiar to you already since you've already seen this type of rotation. But what's important here is recognizing the pattern of when to do the left-right rotation, and that is if you have a left heavy but the left child is right heavy. So earlier it was because we only did one rotation because it was left heavy and the left child was also left heavy, or left heavy and the left child was balanced. Okay, so only one rotation. But if it's left and then right heavy, then we'll do a left-right rotation. Okay, so it's just about recognizing patterns and applying the correct type of rotation. Now, how about if it's right heavy? So you'll know that it's right heavy if the balance factor of the violating node is 2. So if it's 2, it's positive, so it's right heavy, right? And then if you check the right child, if it's either balanced or also right heavy, so they are either it's balanced or the lean is also towards the same direction, then we'll only do one rotation, which is the left rotation, to counter the right imbalance. Okay, so it's just the opposite of the first case earlier. So if we do a right rotation, it would become like this. Okay, so the right child becomes the parent, the violating node becomes the left child, and so on. And then if it's super right heavy, right, because it's right heavy on the V and then right heavy also on the right child, then we'll do also one rotation only, one left rotation. So R becomes the parent, V becomes the left child, and grandchild is still the right child. So you'll notice that the resulting tree or subtree is already balanced in this case by only doing one rotation. But what if it's right heavy and then the right child is on the opposite direction again? So it's right heavy but the right child is left heavy. So it's a right-left forming an angle, and in this case we'll do a double rotation, which is a right-left rotation. So the grandchild would be rotated to the right first to have this, and then the grandchild would be rotated to the left to bring it to the top, and this would be the final form. Okay, so again, this should be familiar to you already if you understand how to do the rotations properly. Okay, so I won't discuss the details of which subtrees became got transferred to another part. Okay, so this should already be familiar to you. Okay, so you do the restructures based on the pattern of left heavy or right heavy, and then looking at the left child or right child and whether it's on the same direction or on the opposite direction. Okay, so to summarize everything in the restructure algorithm, if it's left heavy, you know that because the violating node has a balance factor of -2, and it's right heavy if the balance factor is +2. Okay, now if it's left heavy, you look at the left child. Okay, if the left child's balance factor is -1 or 0, that means that it's in the same direction. So the pattern is just a left leaning slant. Okay, so what you do here is just do a right rotation on the left child. Okay, a single right rotation. But if it forms an angle because the left child is right heavy, so it has an opposite direction, so it forms this angle, then we'll do a left-right rotation on the grandchild. Okay, and then the opposite of that, the right heavy, if it's on the same direction, then it's just a single slant to the right, so we'll counter that with a left rotation on the right child. But if it creates an angle like this, okay, then we'll do a right-left rotation on the grandchild. Okay, so this is the summary of the restructure algorithm. Okay, so let's see some examples of insertion and deletion and see the restructures in action. So given this initial AVL tree, so let's check that everything is you can check that everything has a balance factor of 0, 1, or -1. So if we insert 10 here, where will we insert 10? We'll insert it here, right? Okay, using the normal BST operation. So if we insert it there, right? So insert it here. Let's recompute the height along this path from the new node all the way up to the root. So check its ancestors. So for 10, the balance is still 0 because it has null nodes. For 17, it's also 0 because you have 1 minus 1 here. And then for 44, it's also it's 1 because you have 3 minus 2 here. So it's also balanced. So everything is still balanced. So this is still a valid AVL tree. So we actually don't need to do any restructures here. Okay, because by adding 10, it's still valid AVL. Okay, so yeah, everything was correct. Now how about if we add 1? Okay, so if we add 1, we have that one, we have that one here. Okay, so we'll add 1 here, and then let's recompute the balance factors. So from 1, it's still balanced, right, because it has both zeros. In 5, you can imagine that there's a null node here, so that would be 0 minus 1, so it's negative 1. That's still valid. But here you have a 0 minus 2, right, because this one has a height of 2 already, so that would be negative 2, and that is already an violation. Now based on this violation, what is the pattern that we need to follow? Well, it's left heavy, and the left child is also left heavy, so we can just do a single rotation here by rotating 5 to the right. Okay, so to do that, we'll get this. Okay, so 5 is already rotated, and then let's check all the way up to the root. So this one has a balance factor of negative 1 because you have 1 minus 2, so that's still fine. And then for 44, we have 3 minus 3, which is 0. So everything along this path is already balanced, right? So it has zeros or negative 1s. Now we didn't have to check the right subtree because it did not get affected by adding 1. Okay, the heights of the nodes here remain the same. Okay, those were not affected. So only those along the path from the new node all the way up to the root would be affected. Okay, so yeah, that's inserting 1. And then how about if we insert 54 to this tree here? So where will we insert 54 in this case? We would insert it here, right? So to the left of 62. Okay, so if you know how to insert in a BSD normally, then you'll know that we'll need to search for 54, so it will lead us to the left of 62, and then that's where we insert it. So we'll check all nodes along this path. So from 54, it's still valid. For 62, it's still valid because you have 0 minus 1, that's negative 1, so it's left heavy, that's still fine. For 50, that would be 2 minus 1, so that's 1, so that's right heavy, but it's still fine because it's still 1. And then on 78, you have 1 minus 3, so that's negative 2, so this is already a violation, right? So using this violation, let's try to identify the pattern that we need to use. So it's left heavy because it's negative 2, but the left child is right heavy because you have the positive 1. So we'll have to do a double rotation here. So you have to rotate 62 to the left and then to the right. Okay, so if we do the double rotation, what will happen? So first we'll do the left rotate, and then the right rotate would bring 62 to the top. Okay, so from here, let's check if other nodes along the path to the root are still violating. So 62 is already balanced now, and then 44 is also balanced because you have 3 minus 2, which is 1, and that's still valid. So all of the nodes have are balanced already, so this is now a valid AVL after inserting 54. Okay, now let's take a look at deletion next. How about if we delete 17? So currently this is still a valid AVL because of the balance factors being 0, 1, and negative 1. Now if we delete 17, we find it here. So if we delete that, then we'll check the path to the root. So this is the only one which is already at the root. So at the root, you have this imbalance because if this is the null node here, this one has a height of 1, this is a height of 2, so that's 2 minus 0, so you have 2 as the balance factor here. So this is invalid, right? So the pattern that we can find is it's right heavy, but the right child is left heavy. So since we have an angle, we'll do a double rotation. So we'll have to rotate 50 to the right and then 50 to the left. Okay, so that's our right-left rotation. So if we do that, then the first rotate and then the second rotate, so 50 goes to the top, and then this one is already a balanced AVL tree because all the balance factors are 0. So that is after deleting 17. Okay, now how about if we delete 32 from this tree? So if we delete 32, we'll find it here, right? And so if we delete this, after we delete this, we need to check the nodes 17 and 44 because those are the nodes along the path from the deleted node all the way to the root, and check if they have violations, right? So if we delete that, we'll check 17, still has a balance factor of 0 because null nodes are both height 0, so it's still 0. But for 44, it has a balance factor of 2 because if we compute the heights here, all the nodes at this level would be height 1, nodes at this level would be height 2, nodes at this level, 62 would have height 3, but 17 has a height of 1, right? So that's 3 minus 1 would be 2. So that balance factor is 2. So this is right heavy, okay? It's right heavy here. But what is 62? 62 is balanced, right? Because you have a height of 2 here, height of 2, and then this is balanced. Balanced node. So we'll just do a single rotation, which is a 62 to the left. Okay, so if we do that, okay, 62 is rotated to the left, and so if we check everything, they're all balanced nodes after the rotation. So this is the final tree after deleting 32 and doing the rotations. Okay, so that is insertion and deletion. And so let's check the performance of the AVL tree. So the height of the AVL tree is O of log n because it's mostly balanced, right? Because the height of the node's children should differ by at most 1. Okay, so by enforcing that property, it keeps the tree mostly balanced. So it would have a height of O of log n, so the search would run in O of log n because you're just following the normal BST search. And insert and delete would also run in O of log n because you can do the search in O of log n, and then the restructures will also run in O of log n because you can just do that at the worst case from the bottom level to the root of the tree, right? So O of log n search and then O of log n restructure. So if you add those two together, that's still O of log n. Okay, so that is the idea for AVL trees. You do you insert, and then when one of the nodes along the path from the new node all the way up to the root is violating, then you follow, check the pattern for the restructure, and then do the rotations. It could be a single rotation or a double rotation depending on the pattern. Okay, so that is AVL trees. Okay, now let's look at our third type of balanced search trees. So we're already done with the splay trees, the AVL trees. So the next one would be the red-black trees. Okay, so for the red-black trees, they were created in 1972 by Rudolf Bayer, and the idea is that it's a normal binary search tree wherein the nodes are colored either red or black, hence the name. Okay, now if you have null nodes, those are considered black, but for simplicity, I won't show you the null nodes in the trees so that we can keep our illustration simple. But just imagine that if the null nodes are there, they would be black as well. Okay, and it follows 3 rules or 3 properties that will keep the BST balanced. So what are the 3 rules for the red-black trees? So you have the following. So the first one is the root node should be black. Okay, that's the first one. So that's the root property. The root is black. Second one is a red node's child, or the red node's children, should also be black. Okay, so we'll call this the red child property. So this tells you that there should be no double red. So if it's a red parent, you can't have a red child as well, because the red node's children should be black. Okay, so no double red. And then finally, we have the black depth property, wherein all root to null paths should have the same number of black nodes. So from the root, if you go to the null nodes, along those paths, if you count the number of black nodes, it should be the same for all null nodes. Okay, so using these three properties, it will try to keep the red-black tree balanced. Okay, so let's see if the following trees are valid red-black trees or not. So is this a valid red-black tree given the three properties here? So root should be black, red node should be black, and the black depth should be the same. Is this valid or not? Well, this is invalid because the root must be black, right? And we have a red root here, so this is invalid. Okay, so you have a red root, so that's not allowed. How about this one? Is this a valid RBT or not? Well, it is not a valid red-black tree because you have a double red here. So red's children should be black, but the left child of 42, which is a red node, is also a red node, which is 31. So this is not valid because you have a double red here, so red. Okay, so this is not valid. How about this one? So the root is already black. It doesn't look like we have a double red. Is this valid now? Well, no, still, because the black depths are not the same. So what do you mean by black depth? So for example, the null nodes are here, right? So you have this one, so the squares basically. So we compute the black depth for each node. So for this node, the path to the root will only have one black node, which is 10, right? So there's one here. And then for this null node, it's also 1, which is the 10. For this null node, we have 2, because if you go from the root to the null node, we pass by 10 and 31. Okay, so there's 2 here, there's also 2 here, and for this one, there's also 2, 2, 2, 2, and 2. But for this nodes here, that is because they pass by 64 and 10. For these nodes here, it's because they pass by 31 and 10. But the black depth property tells us that all root to null paths should have the same black depth, but everything here has a depth of 2, everything here has a depth of 1, so they're not equal, so this is invalid. Okay, how about if we change this to black? Will that become a valid red-black tree now? Well, this one is already valid because this time the nodes here would have a black depth of 2, and then the same for all nodes here, black depth of 2, and then there are no red, double red nodes, or the root is also black, so all three properties were satisfied. So this is a valid red-black tree. Okay, so just need to check if all three properties are satisfied or not. Okay, so let's go to the operations for red-black trees. So for search, we'll actually just do a normal binary search tree search. Okay, just follow the procedures of the normal BST search. But for insert and delete, we'll also start by doing the normal BST insert and delete. However, by adding a new node or deleting an existing node, this could violate the RBT properties, or the red-black tree properties. Okay, so this could destroy the tree being a valid RBT. So what we'll do is we will fix those violations by doing recoloring and rotations. Okay, so rotations is still a part of the equation here. So again, let me reiterate that rotations are a very important concept for binary search trees, because without them, you won't be able to understand the rest of the balanced search trees. Okay, so red-black trees are also self-balancing because every time that you insert and delete, it will do recoloring, rotations depending on the situation, so that you will keep the tree somewhat balanced and still follow the three properties of the red-black tree. Now, we'll only discuss the insert part of red-black tree because the deletion has more cases, like, but the concept is still the same. If you have a violation, you do recoloring and rotation to fix the violations, okay? But there's more cases, 6 cases, but you don't really get much out of it. So we'll just discuss the insertion for red-black tree, and yeah, so let's see how to do a insertion in red-black trees. So first, we'll do a normal insert, okay, just like in normal BST. Okay, so we'll have a new node. Okay, now this new node, what should we color it? Should we color it red or black? Okay, if we color it red, this might violate the red child property, right? Because what if the parent of the new node is also red? So if you color it red, that would be a double red. Okay, but if you color it black, this might also violate the black depth property, because if you add a black node along the path, then it would change the black depth of the null nodes, right? So it won't be the same with the rest. Okay, so which one do you think is better, red or black? Well, it turns out you need to choose the lesser of two evils, which is coloring the new node to be red. And the reason for this is because if you violate the red child property, this is just a local error. It's just between the red parent and the red child, right? So it's a local error, so it's very easy to fix. But if you violate the black depth property, this is a global error because it involves all of the root to null paths. So you might need to adjust the other paths as well, so that you could compensate for the added black depth for this new node. So it would be much harder to do. So let's just go with one that's easier to fix, which is we can just violate the red child and then fix it. Okay, so we'll color the new node as red. Okay, so all new nodes would be colored red. And then what will we do after that? So after coloring it red, there would be several cases. Okay, if that was the root and you colored it red, then that would be wrong because the root should be black. So if it's the root, if the new node is the root, then there's only this node as the node in the tree. So it's only one node in the tree. Then we'll just recolor it back to black, okay, to fix the root property violation. Okay, so if it's only this one and you colored it red, if it's the root, then you color it back to black. Okay, now the case 1 is if the new node's parent is black. Okay, so if you added it to a black parent, then you don't need to do anything, okay, after that, because there would be no violations. Why is that? Because, well, if it's not the root, then you won't violate the root property, right? And you also won't violate the red child property because the parent is black anyway, so you're assured that it won't be a red, okay? And then you also won't violate the black depth property because you did not add a black node, so you did not add to the black depth. Okay, so the black depths are unchanged. Okay, so the easiest case is if the parent is black, because you don't need to do anything. Okay, there are no violations. Now for case 2, what if the new node's parent is red? Okay, so if the new node's parent is red and then the new node is red, so that would be a red succession, right? So it violates the red child property. So because of this, we have to check several subcases as well. Okay, if the parent is red, what can we say about the color of the grandparent? Well, the color of the grandparent would have been black, right? Because otherwise, it would have violated the red child property. So we're assuming that the tree that we're currently working with is a valid red-black tree. So if the parent is red, okay, if the parent is red and then this is the new node, okay, the parent of the parent, which is the grandparent, should have been black, right? Because if this was red, if this was like this, then this would have been a violation already. Okay, so this is not a valid BST already. So we are sure that the grandparent is black in this case because the parent is already red. Okay, so yeah, we are assured that the grandparent is black, but we will check the two subcases based on the uncle's color. What is the uncle? So the uncle is, so you have something like this, right? So you have the red node, and for case 2, the parent is red. So the parent P is red, and then we know that the grandparent is black. Okay, now we will have to check what is the color of the uncle. The uncle is here, basically the sibling of the parent. Okay, so the other child of the grandparent. So it could also be that the uncle is on the left child and then the parent is on the right child. Doesn't matter, but basically the sibling of your parent, that is the uncle. Okay, so we'll check two subcases for case 2 based on the color of the uncle. So case 2A is when the parent is red and the uncle is also red. So both the parent and the uncle are colored red. Okay, so they have the same color. So what should we do here? So what we'll do is we'll just recolor the parent and uncle to be black. So they're both black now, and we'll recolor the grandparent to be red. So basically what we do here is, so this is the pattern, right? This is the pattern. You have a parent that's red, an uncle that's red. So on the same level, they have the same color. And then the grandparent is black because we're assured of that. So basically we just switched the colors of this level and this level. So the black became the second level color, and the red became the first level color here. Okay, so we just switched the colors of this, and this will now have no violations for the double red because now your the new node's parent is black, and then it also doesn't violate the black depth property. Why is that? Because along the path here, so originally this was the path, right? So for the paths here, they would have 1 for the grandparent, and then for the path here, they also pass through 1 because of the grandparent. Now after recoloring, the path here would still have 1 because of parent here, and the path here would still have 1 because of the uncle here, right? So basically by moving the black color down and distributing it to both children, okay, so we did not affect the black depth because we both gave the black color to both children. So even if it's the left path or the right path, they'll still have the one black node still, even if we changed the grandparent to red already. Okay, so it's a simple recoloring if this is the case. Okay, if the parent and uncle are both red, so we'll just switch the color of the parent and uncle to become black, and then the grandparent becomes red. The problem here is it could propagate the double red violation upward if the grandparent's parent was also red. Like for example, what if this was also a red, the let's call it A for ancestor, right? So if the ancestor was also a red node, which is possible, right, then by doing that, the double red is propagated upwards to the grandparent and its ancestor. So what we could do in this case is just continue doing the checking of violations upward until either we see no violations or we've reached the root. Okay, so if it violates the double red violation, we'll just continue upwards until we see the root or we find that there are no more violations. Okay, but it's just a simple recoloring, okay, which could propagate the double red violation upward. Okay, so that's case 2A. How about case 2B? This is so before we go to case 2B, let's see all the possible patterns of case 2A. So we showed this one earlier, but what if it's instead of being the left child, it's the right child? It's the same. Okay, so the direction does not matter as long as you have a red parent and a red uncle right here, then you'll just do the recoloring of the levels. And then the same thing if the parent is the right child and not the left child, it's the same pattern. Okay, so the directions don't matter as long as you have the red parent and red uncle, then just do the recoloring. Okay, so that's the full set of possibilities for case 2A. Now how about case 2B? For case 2B, this is when your parent is red but your uncle is black. Okay, so they don't have the same colors anymore, so we can't do the recoloring. So what we'll do here is something like this. Okay, so these are the four possibilities. So your new node is here, you color it red, your parent is red, but then your uncle is black. And then the same thing here, new node is red, parent is red, uncle is black. So all four cases here have that configuration. New node red, parent is red, uncle is black, and then the grandparent, which is always black, is also black. So based on the direction, okay, based on the pattern, we'll have to do some rotations and then recoloring. Okay, so based on the pattern, if it's like this, so if it's double left, so if it's a left parent and then left new node, then we'll do a right rotate. So rotate P right here, so P is rotated once to the right to counter the left heaviness. Okay, if it's right heavy like this, okay, so the parent is a right child and then the new node is also a right child, so they're both on the same direction, which is right, then we'll have to do a single left rotate to counter the left heaviness or the right heaviness. Okay, so if you rotate P to the left, then P becomes the top node and then G becomes the child. Okay, but if there's an angle like this, so new node is the right child of a left child, or here if it's the left child of a right child, then we'll have to do the double rotate. So based on the pattern, we'll do a left rotate and then a right rotate here, or a right rotate here and then a left rotate here. Okay, so it's a left right or a right left depending on the pattern. Now after rotating N to the top, N is here already and N is here also, then we'll have to do the recoloring. Okay, so the top level nodes would be black, the next level nodes would be red, and then the one at the bottom is still black. Okay, so after doing the rotation, recolor depending on the levels. So black and then red and then black. So in this case, it's P and G that's being recolored because you'll notice P here was red and G was black, but after rotating, P became black and G became red. Okay, same thing here, P was red, G was black, and then after rotating, P became black and G became red. Okay, but in the double rotations, it's N and G that you are recoloring. So N was red, G was black, but here N became black, G became red. Okay, so it depends on the levels basically. So first level black, second level red. Okay, so those are the four possibilities for case 2B. So do the correct rotation depending on the pattern, then after that do the recoloring based on the levels. Okay, so yeah, that's case 2B. So the summary of insertion in red black trees are as follows. So for case 0, you added the node as red, but it's actually the root, so I'll just recolor the root as black. Okay, for case 1, if you add a red node to a black parent, or the grandparent could be anything, as long as the parent is black, then you don't have to do any additional action. Okay, because it doesn't violate anything. But if the red node has a red parent and a red uncle, then you just do the recoloring. So you switch the colors of the parent with the uncle and the parent and the uncle, and then switch that with the grandparent. Okay, and then for 2B, if you have a red node, red parent but black uncle, then you'll do the rotations based on the pattern and then do the recoloring. Okay, so that's the summary for insertion in red black trees. So let's see an example of creating a red-black tree from scratch. Okay, so we'll try to insert this five keys to an empty red-black tree, and we'll actually see all cases in this example, right? So when we insert 25 to an empty tree, then we add a red node 25, but since it's the root, then we'll recolor it to 25 black. Okay, so it's a black node now, which is the root, so that is valid. Now if we add 10 here, where will we add 10? We'll add 10 here to the left, right? Okay, so that's the next node supposedly. So for this one, this is the case of 0, which is the root. Okay, for this one, when we add 10, does this have a violation? No, because the parent is black. So if it's a black parent, there are no violations, and indeed the root is black. There are no red successions. The path to root to null paths all have the same black depth. Like for example, here you have a null node here, right? You also have a null node here and a null node here. So the black depth of this is 1, black depth of 1, black depth of 1, because you have the black node, which is 25, which passes through all of these paths. So this is a valid red-black tree. Okay, now after inserting 10, we'll insert 5 next. So where will we insert 5? So we'll insert 5 here, right, to the left of 10. But if we insert 5 here, there will be a red violation. So what will happen there? So if we insert 5 here, there's a red violation. But let's check the uncle, right? The uncle is a null node, which is, as we know, null nodes are black. So this is case 2B. Okay, red parent, black uncle. So we'll do a rotation. But what kind of rotation? So this is a left child. So we'll just do a single right rotate because they are in the same direction, right? So this is a right rotate on 10. So 10 becomes the root, 5 becomes still the left child, and then 25 becomes the right child, and then we'll recolor. So you rotated 10 and then recolor 10 and 25, so that 10 becomes black and 25 becomes red. And then this one is already a valid red-black tree because the root is black, and then for the there are no red nodes, right? And then for the null nodes, the black depth is all 1 also, right? Because you only have 10, which is the root, as the black node. Okay, so this is a valid red-black tree. Now after inserting 5, we'll need to insert 3. So where will we insert 3? We'll insert it here, right? And then for 3, this is still again this is another red violation. So what will happen there? So it's a red violation, right? So let's check the case. So what case is this? So it's a red parent, but it also has a red uncle. So we'll just do a simple recoloring. Okay, so since we can use case 2A here, so the color of 5 and 25 would become black, and then the color of 10 would become red. Okay, but are we done? Well, the 10 is the root, but it's colored red, so this is wrong. So we'll just recolor it back to black. Okay, so yeah, that's why we recolored 10 back to black. So when you see a violation like this, that the root is colored red, you can just recolor it back to black, and that will not violate anything, because by adding it to black, it will it doesn't violate the root property because you've turned the root to black. It doesn't violate the red property because, well, you just turned it to black, so there's no way that you would violate the red, right? And then for black depth, you add 1 to all black to all root to null paths because you just turned the root to black. So all paths will have +1 depth because of this new black node here at the root. But all paths will get this because it's at the root. Okay, so yeah, you can just turn it into black if the root is colored red. And finally, when we add 4, where will we add 4 here? So 10, it's 4 is less than 10, so we'll go to the left. 4 is less than 5, so we'll also go to the left. But 4 is greater than 3, so we'll add 4 here, right? So what case is this? So you have a red parent, but then you have a black uncle, right? Because this is a null node here supposedly. So the uncle is black, which is null. So what will happen there? Okay, so let's check. So we added 4 here. So what will happen is, let's check the pattern. It's a red parent with a black uncle, but the pattern follows an angle, right? So it's right child of a left child. So this would be a double rotation. So we'll do a left rotate and then a right rotate here. So this becomes 4 and then 3 and then 5, which is what we have here. And then do the recolor to have 4 as black and then 3 as red and 5 as red. So after that, everything looks fine because the root is black, there are no red, and then the black depth is the same because for the null nodes here, which are actually black, so just assume that those were colored black. So let me recolor them black so as not to create confusion. The black depths for all nodes, null nodes, are 2, right? Because for this sub 3 you get 10 and 4, and for this sub 3 you get 10 and 25. So there are 2 black nodes for each path. Okay, so we've seen all cases in action. So from the root to having a black parent and then a red parent with a red uncle and then red parent with black uncle using a single rotation and then double rotation. Okay, so that is insertion for red black trees. And as I mentioned, we'll just keep our discussion in insertion for red black trees because the deletion has more cases that doesn't really give you anything new. It's just basically restructuring and recoloring still. Okay, so by following the 3 properties, it keeps the red black tree mostly balanced. Okay, and it's self-balancing by doing recoloring and rotation. So by doing rotation, it keeps the tree balance, and by doing the recoloring, it allows you to follow the 3 properties, the 3 coloring properties. So this will keep the height of the red black tree as O of log n, and with that the search, insert, and delete will also run in O of log n because the height is O of log n. So it's more or less the same with most balanced search trees, right? If you keep the height O of log n, then the 3 operations, search, insert, and delete, will also run in O of log n because they're using the basic search, insert, delete for BST as the basis of their operation, and then they just do additional operations on top of that, but those just take constant time or also log of n time. Okay, so for red black trees, the performance is still O of log n for all 3 methods. Okay, so even if we did not discuss delete, it still runs in O of log n if you do the correct recoloring and rotation. Okay, so that is red black trees. And finally, we have the last balanced search tree, which is 2-4 trees. So it's not a 3-4-2 promo, it's 2-4 trees. It's not 2 or tres, it's 2-4 trees. It's not 24 trees, it's 2-4 trees. Okay, so enough with those lame jokes. Let's discuss 2-4 trees. So 2-4 trees are also known as 2-3-4 trees, are perfectly balanced trees. Okay, so when we say perfectly balanced, there are no holes in any of the levels. Okay, so all the leaves are at the bottom level. Okay, so it's perfectly balanced And so because it's perfectly balanced, the tree height is guaranteed to be O of log n. Okay, so because the tree height is O of log n, we can do search, insert, and delete also in O of log n. So what is the catch here? If it's perfectly balanced and there was a tree that was like this, why did we have to learn splay trees and red-black trees and AVL trees if there was a perfectly balanced tree that was already existing? Well, the drawback here is that it's not a binary tree. Okay, it's a 2-4 tree. So how does it look like if it's not a binary tree? Well, the nodes of a 2-4 tree could have 2 children, 3 children, or 4 children. That's why it's called 2-4 trees. Okay, so 2, 3, or 4 children. So the node could store one entity or one entry, 2 or 3 entries. Okay, so if it stores one entry, we call it a 1 node. If it's 2 entries, a 2 node, or 3 entries, a 3 node. So if it has 1 entry, it will have 2 children. If it has 2 entries, 3 children, and 3 entries, 4 children. Okay, so the number of children would be entries plus 1 or nothing. So if the children are incomplete, you don't you don't have any children at all. So it's all or nothing. Okay, so you either have the full set of children or you don't have any children, because as we said, 2-4 trees are perfectly balanced, so there should be no holes along any levels. Okay, so yeah, that's the properties of 2-4 trees. So lastly, the node entries should be sorted. So you have 1, 2, or 3 entries, right? So the nodes here should be sorted in ascending order. So these are how the nodes in 2-4 trees look like. So if it's a 1 node, then there's only 1 entry, right? So it has 2 children, and those to the left are less than A, and then those to the right are greater than A. Okay, so this is just like your normal BST nodes, because this is also binary node because it has 2 children. But what if it's a 2 node or a 3 node? Okay, if it's a 2 node, this should be sorted, so A should be less than B. Okay, and then it has 3 children. If it has 2 entries, 3 children, right? So the first set of children here would be less than A. The second, which is in between A and B, would be greater than A but less than B. Okay, so basically in between the range of A and B. And then the one who's on the rightmost would be greater than B. Okay, and then for 3 node, it's basically the same idea. So it has 3 entries and then 4 children. So the one at the leftmost would be less than A. The one in between A and B would be greater than A but less than B. The one in between B and C would be greater than B but less than C. And the ones to the right of C would be greater than C. And A, B, C are in order. So A is less than B and less than C. Okay? And as I said, the children would be all or nothing. So either you have both children, or all 3 children, or all 4 children, or you don't have children at all. So if one of them is missing, then it's not valid. Okay? So yeah, that's 2-4 trees. So this is an example of a 2-4 tree in action. An example. So you have let's identify the 1 nodes. So you have 1 nodes here, 14. Okay, so let me change to another color. So for 1 nodes, I'll use orange. So 1 nodes are 14, 32, and then mostly the ones at the leaf, 10, 18, 25, 33, 42, 47, 74, 81, and 43. The 2 nodes, we actually only have 1. I'll use this color. The 2 nodes are here, so they have 3 children, right? And for going back to our 1 nodes, they either have 2 children or no children. Right here, they have no children, right? So they have 2 children here, 2 children here as well. Then the rest, the ones at the bottom level, don't have any children because they are leaf nodes, right? For our 2 node, they have 3 children. And then finally for our 3 nodes right here, they have 4 children, which is here, 1, 2, 3, 4. And then another 3 node here, but it doesn't have any children because it's at the bottom level. Okay, so that's an example of a 2-4 tree. Okay, so 2, 4 trees follow two properties. So first is the size property. So the nodes either have 0 children or 2, 3, or 4 children depending on the number of entries. So if it's entry 1 entry, you have 2 children. If you have 2 entries, 3 children. If you have 3 entries, 4 children. But if it's incomplete, then you don't have any children. Okay, so it's all or nothing. And then the second one is the depth property, which tells you that all leaves should be at the same level. So going back here, all the leaf nodes or those with no children are at the same level, which is at the bottommost level. Okay, so that makes it a fully balanced tree. Okay, but it's not binary because you could have 3 or 4 children. Okay, so how will we do search for 2, 4 trees? So if you search for key K, we'll start at the root and then we'll check if any of the nodes are what we are looking for. Okay, so at that node, since it has either 1, 2, or 3 entries, are any of those entries have the key that we're looking for? Okay, if not, then we'll proceed going down. Okay, but if it's found, then you return it. Okay, if it's not found, you go down to the child where K could be based on the range. Okay, so based on the is it less than A, is it between A and B, is it between B and C, or is it greater than C, something like that. So based on the ranges, go to the appropriate child. Okay, and then you repeat this until you've either found the key that you're looking for, or you get stuck, or you get you find a dead end because the node is already a leaf and there are no more children, and that's when you stop and then say that it's nowhere to be found. Okay, so yeah, that's the search procedure for 2, 4, 3. So it's basically similar to the normal BST search, but you just extend the search procedure because now you could have 2 children, 3 children, or 4 children. Okay, so yeah, so let's see an example. If we search for 79, starting from the root, it's not in any of the root, but 79 is greater than 50, so we'll go to the right child of 50 right here, and then at this node 70, 79, we found it, so we return it here. Okay, how about if we search for 74? So we start at the root node here, 20, 40, 50. It's greater than 50, so we'll go to this child here. 70, 79 is it's not 74 is nowhere there, but where should we go to? So it's between 70 and 79, so we'll go to the middle child, which is 74, and luckily we find it here. Okay, so search 74, and then how about if we search for 19? So if we search here, 20, 40, 50, it's not in any of this, and you can even stop earlier because from 20 you already know that 20 is greater than 19, so you should go down to the left child already. And then for 14, 19 is greater than 14, so you should go to the right child. And then it's 18 here, 18 is less than 19, so you should go down, but there's no more nodes below this level because it's a leaf node. So we'll stop here and we'll say that 19 is nowhere to be found, because if it was, then it should have been here somewhere, right? So we did not find 19 in the tree. Okay, so that is search. Now how about for insert? Okay, so here's the overview for insert. We'll first insert the key K and value V into the 2, 4, 3 by finding a leaf node to insert into using search. Okay, so we'll either search for it, assuming that it's non-existent. Okay, we'll find the leaf node to insert into, because if it already exists, then we'll just overwrite it. Okay, so we'll find the leaf node to insert into using search K. So just like what we did here. So for example, if we were to insert 19, then we'll follow this path and find the leaf node where 19 should have been, right? But since 19 does not exist, then we'll probably insert it here, okay, in this node here. So that's the leaf node. Okay, so we'll find the leaf node to insert it into, but the problem is when we run into a 3 node. So remember, a 3 node is a node that already has 3 entries. So A, B, and C. But if you add K here, then this will become a 4 node, which is invalid. So that would cause an overflow. Okay, so it's more than what we are allowed to have. So if you have a 3 node already and then you add one more entry, it will create a 4 node, which causes an overflow. So we need to fix that. Okay, so the solution is, during the search process, whenever you encounter a 3 node, okay, even if it's not yet the leaf that you're looking for, so whenever you encounter a 3 node, you split the 3 node by putting the middle key in the parent node. So we call this the split operation. Okay, so how does that look like? So here you encounter a 3 node, right? So we'll split this 3 node by elevating this middle child here to the parent. So 11 became a part of the parent. So the parent now has 11 and 20, and the 2 remaining children, the 2 remaining keys here would be split into single nodes. Okay, so from a 3 node, you have A, B, C. B gets elevated to the parent, so B will have will be already part of the parent, and then the remaining 2, A and C, would become 1 nodes, wherein the link would be like this. Okay, so after elevating this middle key here, then you still have the links to these 2 children. Okay, and then if they have more children, then it would be split like this: A, B, and then C, D. Okay, so that is the split operation. You elevate the middle key to the parent, and then you get 2 1 nodes as the child. So why would we do this? Because we don't want to have any 3 nodes during insertion, so that when we insert, there is space to insert into. We are assured that there won't be any overflow. Okay, and we are assured that the parent node also has room for the elevated middle key, since we check the parent node going down and check if it needs to be split or not. Okay, if we did not split the parent, that means that it was a 1 node or a 2 node, so we have room for 1 more. Okay, but if we did split the parent, then that means that the parent is now a 1 node, so we have more room to add it into. Okay, because the worry is that we elevated this key upwards, but what if the parent key doesn't have room? Well, we are assured that it has room because we also did the same to the parent going down, right? So since we start at the root, and then whenever we encounter a 3 node, we split it. So we are sure that the parent is not a 3 node anymore, because if it was, then we would have split it already, right? So we are assured that the parent has room for the elevated middle key. Okay, so that's the idea here. So let's see an example. If we try to insert 16, so we'll start at the root, but we encountered the 3 node, so we'll split it. So we'll elevate 40 upward, and this will become the new root node. Okay, so we split 20, 40, 50. 40 becomes the new root, and 20 and 50 becomes 1 node. And then we'll continue with 20 here, and then we'll go to the left because 16 is less, and then we'll go to the right of 14 because it's greater than 14, and then we find the leaf node. So this is safe to insert here because it's a 1 node, so we'll just insert 16 here, and then insert it to the appropriate position, because we have to keep the keys sorted, right? So 16 is inserted here because it should be less than 18. Okay, how about if we insert 99? So if we insert 99 into this tree, we start at the root, and then we encounter a 3 node, so we'll split it again, so to 40, and then 50 is 99 is greater than 50, so we go to the rightmost child, and then 70, 79, 99 is greater than 79, so we go to the rightmost child, and then we reach a leaf node, and then we can safely insert it here because it's a 1 node, so 99 is inserted here next to 81. Okay, how about if we insert 60? So the same process, split 40 upwards, and then 50 60 is greater than 50, so we'll go to the right child, and then it's less than 70, so we'll go to the left child. But then we find a 3 node here, so we'll split it. So what will happen? Because we cannot insert 60 yet here because it's a 3 node. So we'll split this by elevating 62 here. Okay, and then we'll have 2 nodes here, 57 and 66. Okay, so that is the next step. So 62 was elevated, and then the 2 were split, and then we'll insert 60 here on the correct node, because 60 is less than 62, so we'll go to the left, right? So 57 and then 60, so we inserted 60 here. Now you'll notice when we elevated 62 upward, it created a new 3 node here. Now should we also split that or not? Well, it turns out we don't need to concern ourselves with that one already. So if a new 3 node is created after elevating the mid child, you don't need to split it because we're already past it anyway. So we're already at the next level. So that would be a problem for the next insertion. Okay, so yeah, we just made sure that there was a room for the parent node whenever there is a middle child that we need to elevate. But if it creates another 3 node, it doesn't really matter because we're already at the next level. Okay, so that's a problem for the next insertion. So insertion can increase the tree depth by splitting the root, which is what we've seen by doing the splitting of the initial 20, 40, 50 root node. So the tree could could increase the height by creating a new node when we split the root node. So that is the only time we increase the depth, because every time we insert at the leaf, we make sure that the leaf does not have the leaf has enough room for us to insert into. Okay, so that's the only time we increase the tree depth. So again, on insertion, whenever we encounter 3 nodes, we split them on the way down to make sure that there's room for either the new key to insert into if it's a leaf node, or if it's an internal node, we make sure that there is enough room for the elevated key when we split, whenever we encounter something at the next level. Okay, so yeah, that's the reason for splitting the 3 nodes, is to make sure that there's room for the new key at the leaf, or when we want to elevate during splitting in internal nodes. Okay, so that is 2, 4, 3 insertion. So let's try to create a 2, 4, 3 by inserting from scratch. So this is the process. So okay, so I added it all to one panel, but we'll have to go through each one in detail. So at the start, if it's just blank, we would have added 4, and then after adding 12, it would have become 4 and 12 like this, and then adding 6, it becomes 4, 6, 12, right? And then from here, if we add 15, where would we have added 15? So we'll start here, but then this is a 3 node, so we'll split it. So this becomes 4, 6 here. So maybe I'll reduce the size of this, of the pen. So we'll start here, right? So this is a 3 node, so we'll split it. So 6 becomes elevated to the parent, and then we'll have 2 nodes here, so we'll delete that right there. And then where will we add 15? We'll add it here, right? So we'll add 15 right here, and that's valid since this is a 1 node anyway, so that's why you add 15 right here. Okay, now if we add the next node, which is 3, where will we add that? So we'll start at the root 6. This is not a 3 node, so 3 is less than 6, so we'll go to this branch here, and this is a leaf node that is a 1 node, so it's valid to add 3 here, so we'll just add 3 here. Okay, so 3 was added at this node right here. So the next node that we'll add is 5. Okay, so where will we add 5? So we'll search, we'll start at 6, that's fine. 5 is less than 6, so we'll go to this branch, and then this is already a leaf node, which is a 2 node, so there's room to add 5 here, so we'll add 5 here. So 5 was added here. Okay, the next node that we'll add is 10, so we'll add 10. So we'll start at the root. 10 is greater than 6, so we'll move to this branch, and we find the leaf node that is a 2 node, so there's still room for 10 here, so we'll just add 10 right here. Okay, so far everything has been simple, right? But now, what if after adding 10, we'll add 8. Okay, so we'll start here. 8 is greater than 6, so we'll go here, but this time it's a 3 node, so we'll have to split it. So 12 will be elevated because that's the middle child, so 12 is elevated, and then you have 2 nodes here, 10 and 15. So the parent is extended, it becomes 6 and 12 now. So the 2 children are 10 and 15, and then we'll insert it into the appropriate node, which is 10, so to the left of 10, which is 8. Okay, so you added 10 as 8 to the left of 10. Okay, so after that, after inserting 8, what if we insert 1? Okay, so we start here. 1 is less than 6, so we should go to this branch, but then we encounter a 3 node, so what we'll do is we will split it. So we'll elevate 4 to the parent, so it becomes like this. So let me erase this, and then it becomes, so 4 is no longer here, and you have 2 new nodes here like that, and then you'll add 1 right here, so you have 1 next to 3, then you have 4, 6, 12 as the new root, and then you have 1, 3, and then 5, 8, 10, and 15. Okay, so after adding 1, we'll add 9 next. So we'll start here, but this is a 3 node, so 6 gets elevated as the new root, then this becomes split, right? And then where will we go? 9 is greater than 6, so we'll go to this branch, and then 12 is 9 is less than 12, so we'll go to this branch here. So we added between 8 and 10 right here, so we added here in between, so that's why 9 was added in between 8 and 10. Okay, and finally after adding 9, we'll add 7, so we'll start here. 7 is greater than 6, so we'll go to this branch. Less than 12, so we'll go to this branch, but then we encounter a 3 node with 8, 9, 10 here, so we'll do a split. So we'll elevate 9 upward, right? So 9 becomes part of the parent, and then you have this node here, so 9 is no longer there, then this node here, and then 7 is less than 9, so we'll go to the 8 branch right here, and then insert 7 right here. Okay, so that is how you insert in 2, 4, 3. So whenever you encounter a 3 node, you split it, and then until you find go down until you find the leaf node where you can safely insert it into. Okay, so yeah, that's insertion in 2, 4, 3s. Now, how about the deletion in 2, 4, 3s? So here's the overview. We'll find the key K using the search procedure, and we'll come up with a node, right? It will return a node. If we find it in the leaf node, we'll just delete K, but if the key K is an internal node, we'll replace it with the next higher key, so the in order successor, and then we'll delete the next key. So this is like what we did in the deletion of the normal BST, right? So if it doesn't have any children, we'll just safely delete it, but if it has 2 children, or it's an internal node, then we'll look for the next key. Remember that. So you go to the right and then go left all the way to get the next higher key, or the in order successor, and then we'll swap them and then delete the next node. So it's similar to that process. Okay, now the problem when doing this is, what if we delete a 1 node? The reason for this is because we cannot delete a one node because it becomes empty, right? And since there shouldn't be any blanks because the children should be all or nothing, then we cannot allow this to happen. So if you have a one node and then you delete one entry from it, it becomes a zero node, which is an underflow. And recall, the children is all or nothing, so we can't have any zero nodes lying around. So what we'll do is, during search, we will eliminate one nodes that we encounter along the way, except for the root. Okay, so if it's the root, then we'll just keep it as a one node. We won't delete the root anyway. Okay, so but if it's not a root, then we'll have to eliminate them using some rotations and fusions, and yeah. So we'll look at several cases. This is case 0, the normal delete. If the node is a 2 node or a 3 node, okay, so we'll just delete key K because we have enough room for it to delete. So if we delete from a 2 node, it becomes a 1 node, so that's safe. If we delete from a 3 node, it's a 2 node, so it's also safe. So we won't create a 0 node in this case. So we can just safely delete the key K, and it will not cause any underflow, okay, because we have enough keys that will be left. Okay, but what if the node is a 1 node? So if we delete from this, it becomes a 0 node, so we have to do something here. And the parent is a 2 node or a 3 node, and the adjacent sibling is also a 2 node or a 3 node. So what we'll do here is something called a rotation or a transfer, and this is possible because we can afford to borrow from the parent and the sibling. So if we can afford to borrow both from the parent and the sibling because they have 2 or 3 entries, then we'll do a rotation or a transfer. So how does that look like? So a rotation transfer looks like this. Okay, so the node that will rotate is highlighted here in yellow, right? And the parent is a 2 node or a 3 node, so it can afford to give you 1. And the adjacent sibling is also a 2 node or a 3 node, so it can also afford to give you 1. So what we'll do in this case is we'll do a rotation. So we will bring down a key from the parent, okay, to the 1 node, and then we will elevate the key from the sibling to the parent. So that is the rotation. Okay, so the 40 here from the parent will be elevated, will be brought down, so it becomes together with 30 here, so 40. And then to take the place of the parent's key that was brought down, we will elevate 1 key from the sibling. Okay, so we bring this down from the parent and we elevate this one from the sibling. So this was from the parent, this was from the sibling, and that is because we could afford to borrow both from the parent and the sibling. Okay, so that is the rotation. And then when this is already done, we can now safely delete 30 because it's already a 2 node. Okay, so the parent is still valid, the sibling is still valid, and we do this rotation keeping the ranges still intact. Like even if we rotated 50 upwards, everything here is still between 20 and 50, and everything here is greater than 50 because we rotated the leftmost part of the sibling. Okay, so yeah, so that is case 1, when both the parent and the sibling can afford to loan you a key. But what if only the parent can afford to give you, or can afford to borrow, to let you borrow? So this happens when you are a 1 node, okay, and the adjacent siblings are also 1 node, so they cannot afford to let you borrow because otherwise they will also be underflow. Okay, but it's the parent that can allow you to borrow, so it's a 2 node or a 3 node. So this time you can only borrow from the parent and not from the siblings. So what we'll do here is something called a fusion. So what will happen? So here in this situation, 30 is what we'll try to delete, but looking at its adjacent siblings, they're all 1 nodes as well, so we cannot borrow from them because if we borrow from 10, this will become underflow. If we borrow from 50, it will also be underflow. So we can only borrow from the parent, and what will happen is we will borrow from the parent. This will be brought down, and then we will fuse the sibling, adjacent sibling, and the node, and then the brought down key from the parent, forming a 3-node. Okay, so yeah, that's what will happen. So that's why it's called fusion. Okay, so you bring down the key from the parent, and the 1 node plus the sibling 1 node and the key that was brought from the parent will form a new 3-node, which is found here. So that is fusion. Okay, so now that it's a 3-node, you can now safely delete 30 because there will be 2 entries left still in this node. Okay, so that is case 2. And then the final one is it's also a fusion but at the root. So what if your node is a 1 node, your adjacent sibling is also a 1 node, and the parent, which is the root, is also a 1 node. So you cannot borrow from the parent anymore because it's also a 1 node and it's the root. So what we'll do is we'll fuse the node, the sibling, and the root to a 3-node, and that will form the new root. Okay, so it looks like this. So if the parent is already the root and the sibling is also a 1 node, then we'll just fuse all 3 together to form the new root. Okay, so yeah, that is the case number 3. So in this case, the tree height will decrease by 1 because the root here was fused into the children. Okay, so it decreases by 1. So this is the only time that the height will decrease in the tree. Okay, so putting all of those together, we have the following summary. So in case 0, if it's a 2-node or a 3-node for the deleted node, then we don't have to worry, just delete it as is because there will be enough entries left at that node anyway. For case 1, if you're a 1 node and then you can afford to borrow from the sibling and the parent because they are 2 nodes or 3 nodes, then we'll just do a simple rotation. But if you can only afford to borrow from the parent and not the sibling, then we'll do a fusion. Okay, but if all 3 of them are 1 nodes and the parent is the root, then we'll do a fusion and we'll set that new node as the new root. Okay, but this set of operations are actually kind of open-ended because we're just saying here that it's a sibling, but which sibling should we borrow from? Should it be the left sibling or the right sibling? Okay, so to keep things uniform, we'll do this tiebreaker. Okay, or we'll follow this procedure. So choose the adjacent sibling with the most items. So which sibling has more items that could that they can afford to borrow to loan, basically. So if you have a sibling that is a 3-node versus a sibling that is a 2-node, then you borrow from the 3-node because they can afford to they have more keys to loan you. Okay, so choose the adjacent sibling with most items, but if they are tied, then we will prioritize the left sibling. Okay, so this is our tiebreaker. Choose the one with the most items first, but if they have the same amount of items, then prioritize the left sibling. Okay, so that is what we'll do for the deletion. So let's see some examples. So let's try to delete 62. So here 62 is found at the root node at the 3rd entry, but 62 is a internal node, so it's not a leaf node, right? So we'll find the left, or sorry, not the left, but the next key, which is 70, right? So remember, finding the next key, to find next, we'll go right, then continuously go to the left. So we'll go to the right, which is the right of 62, which is here, and then we can't go to the left anymore because this is the leaf node, so we'll just get the leftmost node, which is 70. Okay, so that is the next entry, so we'll switch that with 62 here, so this becomes 70. That's the next node, and then we'll delete 70, but it's safe to delete 70 here because it's a 2-node anyway, so it will just become 79 after deleting 70 and adding it to 60 here, 62, sorry. So again, why did we do this? Because 62 is a found in an internal node. So what we'll do is replace it with the next key, and the next key can be found by going to the right and then going to the left, dot dot dot, until we reach a dead end. Okay, just like what we did in the normal BST. Okay, that is for 62. How about for 32? Okay, so for 32, we'll start our search at the root node, right? So is this 20? No. Is this 42? No, but we know now that it should be between 20 and 42, so we'll go down, right? And then we find 32, but 32 is a one node, right? So if it's a one node, what will we do? Let's check the parent. The parent can afford to let you borrow because it's a 3 node, so that's fine. How about the siblings? Well, the sibling is a 1 node and a 1 node, so we'll do a fusion here. So where will we fuse? Should we fuse left or right? Well, since it has a 1 node and 1 node, they are tied, so we'll favor the fusion to the left. So we'll borrow from the parent, so this one 20 will be brought down right here, and then we'll fuse this with the left sibling. So that's why it became 14, 20, and 32 here. Okay, and then now, since this is a 3 node already, we can safely delete 32, and the resulting 243 is this one, the final one. So you only have 14 and 20 here, and then the root only has 42 and 62 because we have brought down 20 earlier during the fusion. Okay, so this is an example of a fusion, and we favored the one to the left because they were tied anyway. The siblings were tied. Okay, so this is an example of the tiebreaker. Okay, so let's delete 32. How about delete 7? Okay, so we'll start our search at the root. So 5, it's not 5. 9, it's not 9. But now we know that the 7 is between 5 and 9, right? So we should go down this branch here, and luckily enough we find 7 here, but 7 is in a 1 node. So what should we do? Well, let's check the parent. Can we borrow from the parent? Yes, we can. And we can also borrow from the siblings because there's a 2 node here and a 3 node here. So where should we borrow from? Should we borrow from the left sibling or the right sibling? Well, we will favor the one with the most keys to allow us to loan, right? So we'll choose the one on the right. So we will do a rotation with the right sibling. So 9 will be brought down here, 11 will be brought up. So 11 became part of the parent, 9 became part of the 7's node, and so we did a simple rotation. And so now 7 is not alone, so we can safely delete it. And now the final 243 is like this. So 9 was added here, 11 was elevated here. Okay, so this is an example of a rotation, and we favored the one with the most keys because we could also have done a rotation with this one, but as per our rule, we will choose the one with the most keys that will allow us to loan. Okay, so since this has 3 keys and then this one only has 2 keys, we will favor this one. Okay, so that is delete 7. Okay, now let's see delete 40 from this tree. So we start at the root. The root is a 1 node, right? And we've actually found 40. So we'll actually look for the next hierarchy, right? So what is the next hierarchy? So as I mentioned, we should go to the right and then go left. So go to the right, that's 50, and then go left of 50 is 43, go left 42, and then this is a leaf. So this is the next hierarchy that we'll have. So this is the path that we'll take later. So we will end up replacing 42 here, and we also encountered a 1 node which is 40, but this is the root, so we won't eliminate it, right? But when we go down to the right, it's 50 and it's also a 1 node, so we'll eliminate this, and we'll actually use case 3 here because you have the node, the parent is the root, and your sibling is also a one node, so we will merge this 3 into 1, and this becomes the new root, right? So using case 3, we'll merge them into 3, right? This is the new root now, and then we're going to the left of 50 supposedly, so it's 43, and then we encountered another one node, so we'll eliminate this by doing a, well, let's try to see what would be used. So you have a one node, but you have a sibling that you can borrow from. This is a 3 node here, and the parent is also a 3 node. Okay, so you can do a rotation using case 1. So 50 will be brought down here, 62 will be brought up, so this becomes 62, and then you add 50 right here. Okay, so that would be next. Okay, so after the rotation, you'll go to the left of 43, so you find the 42, but this is a one node, so you'll also need to eliminate this one. But what will we use this time? So the parent has 2 nodes, so that's fine, and then the sibling only has 1 node, so we'll actually do a fusion using case 2, right? So we'll drop 43 down, forming a 3 node here, and then yeah, so that's a fusion for this one. And then we're already at the leaf, so we can now remove 42 and put it in place of the 40 earlier that we removed. So we do that and then safely delete 42 from here, and then that's the final tree. Okay, so that is deletion in 2-4 trees. Now it turns out 2-4 trees and red-black trees are actually related, because a red-black tree is just a binary tree representation of a 2-4 tree. So you can convert from a red-black tree to 2-4 tree and vice versa. So I'll show you how. So if you're given a 2-4 tree, you can just convert it to a red-black tree by following these transformations. So if it's a 1 node, it's just a normal binary tree node. So you can just have the 2 children here and then just the 1 entry at the node. If it's a 2 node like AB here, you can have A as the left child of B, and then A is colored as red, or A is the parent and then B is the right child, because that also follows the order, right? So if A is less than B, then A should be either the left child of B or B is the right child of A, and then you color whatever is the child as red. Okay, and then for 3 node, B would be the parent, and then A and C would be the children, whereas the children are also colored red. So you'll just use these transformations to convert a red-black tree to a 2-4 tree and vice versa. Okay, so let's see an example of that. Given this 2-4 tree here, let's try to convert them into a red-black tree. Okay, so I have the conversions here at the bottom, so we'll use that as a guide. So let's start with the 1 nodes. Okay, so the 1 nodes are colored black, right? So which are the 1 nodes? We have this one, and this one, right? So that would be 5 here, 10, and the 15, right? And then also the 4 is a 1 node, so you have 4 here, and 6 is also a 1 node, right? Okay, now for the 2 nodes, you have AB, so you follow this one, 1 and 3. So the one that is greater will become the parent. So you have 3 here and 1 here, and then you have 7, 8 here, so that's 8 here and 7 here. Okay, so this one is okay. Then you also have the 9, 12, so 9 is the smaller, so I'll have that one here, and then 12 is the bigger, so I'll have that one here. Now how do we connect them? So 9 and 12 is connected, 8 and 7 is connected, 3 and 1 is connected. So 4 is connected to 1, 3, so that's here, and then it's also connected to 5. And then 9 is connected to 7, 8, so that's here. And then it's also connected to 10, and then 12 is connected to 15, and then 4 and 6 is connected to this one, 9 and 12. So this is now our red black tree, and let's check if it follows the red black tree properties. Well, the root is black, okay, there are no red parent, red children, so that's okay. And then for the paths, their depths, let's check. Okay, so let's check the depths of the null nodes right here. So in this path you have 3, right, because you have 3, 4 and 6. Here you also have 3 because it's the same one, 3, 4 and 6. Here you also have 3, 3, 4 and 6. Here you also have 3 because of 5, 4 and 6. Here you have 3 because of 8, 12 and 6. Same here, 8, 12 and 6. For this one it's 10, 12 and 6, so that's also 3. And then here it's 15, 12 and 6, so that's also 3. So all the null to root paths have depth of 3. So this is a valid red black tree. Okay, so we just converted this 2, 4 tree into this red black tree. Okay, so that is here. Then you can review it later, but that is the better version of the illustration. Let's see one more example for a 2, 4 tree into a red black tree. This time it has a 3 node, right? So for the 1 node it's only 15, so that's here. So where can we draw that? Maybe here. And then for the 2 nodes we'll follow this, so it's 8 and 10, so that would be 10 here and then 8 here. And then for 6 and 12 that would be 6 is smaller, right, so maybe here, and then 12 right here. So they are connected here. And then for the 3 node here, 3, 4, 5, we will have 4 as the middle child, and then 3 and 5 as the children. So 4 is the parent, 3 and 5 as the children. So now let's connect them. 6 is connected to 3, 4, 5, so we'll connect that here. And 6 is also connected to the 8, 10 part, so it's here. And then 12 is connected to 15, so that's 1 here. So this is the red black tree. And again, let's check the red black tree properties. Okay, so let's draw the null nodes. So the root is black, so that's fine. There are no red succession, so the red children has black, the red nodes have black children. That's fine as well. So how about the black depth? For this one we have 2 as the black depth for 4 and 12. Same with this one. This one also has 2 because of 4 and 12. For this one, this will have 2 as well because of 10 and 12. And then same with this one, 10 and 12. And for this one also has 2 because of 15 and 12. So everything has the same black depth. So this is a valid red black tree as well. Okay, so if we clear that, you'll have the better illustration right here. Okay, so yeah, that is the 2, 4 to red black tree. Now how about if we do the opposite? What if we try to have the red black tree to 2, 4 tree? Okay, so how will we do that? Okay, so we'll still use the patterns and try to figure out how to combine them. So basically this one here is just a 1 node, right? So that would be 7 somewhere here. This one is a 2 node, right? Because it follows this pattern, black and then red. Okay, so this one will become what, 29, 31? Yeah, and then this one is a 3 node because it follows this pattern right here. So this becomes what, 50, 64, and 83, right? And then this one is a 2 node because it follows this pattern right here. So this becomes 10 and 42. 10, 42. And then let's connect them. So 10 left is connected to 7. It's connected here. 42. 10 and 42 are connected to the 31 here in between. And then 42 is connected to the 64 part. So that's here. So this is the 2, 4, 3. And this is valid because 7 is less than 10. 29 and 31 are between 10 and 42. And then everything here is greater than 42. So this is a valid 2, 4, 3. Okay, so just by figuring out the patterns and doing the conversion, you can create the 2, 4, 3 from the red black tree. Okay, so if we show you the next slide, you'll have the better version. And then one last example for this one. Let's see. So we have the 1 nodes, right? Maybe let's start at the bottom level. So this one would be a 2 node, right? So this is 1, 2. Now this one is not a 2 node. This is actually a 1 node right here. So that is 4. And then you have a 6 here as well as a 1 node. And then what's left is the pattern here, which is a 2 node, which is a 3, 5. Because you have this pattern. Okay, so if you connect them, 3's left is 1, 2, so you have that. 3's right is 4, so you have this. Then 5's right is 6, so you have this. So this is now your equivalent 2, 4, 3 from this red black tree. Okay, so if I remove this, then we'll see the final 2, 4, 3. Okay, so yeah, it's easy to convert a red black tree to 2, 4, 3 and vice versa using the following transformations. Okay, so that's it for binary search trees and balanced search trees. So we talked about splay trees, AVL trees, red black trees, and 2, 4 trees. And that is since this is our last lecture for ComSci 123, then that is also it for our semester. Okay, so let's try to review what we have learned so far in ComSci 123. So first, we looked at the linear ADTs. So we looked at 6 linear ADTs. So you have stack, which follows the last in first out property or method. So the last thing that you insert is the first thing that you push out. So you can only look at the top. You can also only do operations on the top of the stack. Okay, the next one is the queue, which follows the first in first out method. So you insert items at the back and then you remove items at the front. So the first item that you inserted would also be the first item that would be taken out. Okay, so it's just a regular line, a regular queue. Then you also have a deck or a double-ended queue wherein you can add on both ends this time. So you can insert first, insert last, or remove first and remove last. So it's just a double-ended queue. Okay, and then a vector generalizes ADTs that uses a rank. Okay, so the rank is the number of items that comes before you. So B here has a rank of 1 because there's only 1 item before it, which is A. Okay, D has a rank of 3 because it has 3 items before it, which is A, B, and C. So you insert, remove, replace, and get items using their ranks. And then the opposite of that is the list, wherein it's not about ranks but it's about positions. Okay, so what is before me or after me. Okay, so you refer to items before them or after them. So you have methods that are positional. So first, before, insert before, and so on. Okay, so that is list. And then for sequence, it's just a combination of vectors and list, right? So it has rank-based methods and position-based methods, and it also has bridge methods that will convert from rank to position and position to rank. Okay, so that's the combination of vectors and lists. And they're called linear ADTs because they have a unique first element, a unique last element, a unique predecessor, and a unique successor. Okay, but if one of those four properties are not met, then they are called non-linear ADTs. And for non-linear ADTs, we discussed four main non-linear ADTs. So the first two were maps and dictionaries, and they both used the concept of entries, right? Key value pairs. And the main difference is that for maps, you have unique keys, whereas in dictionaries, you can only you can allow same keys. Okay, so multiple entries with the same keys are allowed. Okay, so for map, you need to make sure that the key is unique before you can insert it to the map. Okay, and then we also discussed priority queues, which are also using entries, but this time the keys are used as the priority level. Okay, so instead of like a regular queue wherein it's first in first out, here you remove the entry that has the highest priority first. Okay, so you remove min, get the min, and then insert a new entry with the key being the priority level. Okay, and then we also discussed the tree ADT, wherein it's a collection of nodes that have the parent-child relationship. So you have the root node, which is the topmost level. Okay, you have the parent node, child nodes, you have internal nodes and leaf nodes. The difference being leaf nodes have no children, whereas internal nodes have children. And then we also discussed traversals. Okay, so BFS traversal, DFS traversal. So for BFS, you go layer by layer. For DFS, you go as deep as possible and then backtrack as necessary. And then the three traversals following DFS are pre-order, post-order, and in-order. So you should know this traversals by now. So pre-order goes to the root first and then left and then right. For post-order, it's left and right before the root. And then for in-order, it's left, root, and then right. Okay? So those are the non-linear ADTs. And then for all these ADTs, we implemented them using various data structures, right? So first, we looked at arrays that uses index, and then linked lists that are either singly linked lists or SLL, or doubly linked lists, which are DLLs. So for singly linked list, you only have links to the next node, but for doubly linked list, you have links for both the next node and the previous node. Okay, and then you have sentinels, which are the head guard and the tail guard, which are like double DLL nodes, but they don't store any value. Okay, so they're just there to guard the both ends. Most of the ADTs we implemented using arrays and linked list, but there are also some special data structures that we introduced, like the hash tables. So you have a hash table and a hash function, which supposedly distributes the entries according to whatever the hash function is designed to do. And then we either have a chain of entries in that slot if you're using separate chaining, or if you're using linear probing, then you just find the new entry or new slot to fill in if the initial slot has already been occupied. Okay, so you use this for maps, dictionaries. Then for skip list, you use this for ordered maps. So you apply random heights so that you could skip over some nodes, making the search faster. So by randomizing the heights, you can get O of log n in search as well. Okay, and then for heap, we use this for priority queues. It's a special type of tree wherein the arrangement is that the nodes keys should be less than the children. Okay, so the minimum key should be at the root. Okay, so you use this for priority queues. And finally, we also discussed binary search trees that follows the property no left keys should be less than the node's key, and then the right keys should be greater than the node's key. And then we discussed several balanced search trees like the splay tree, which tells you to splay the root to the splay the node to the root, so that the next time that you deal with that node, it will be at the root or near the root, so it will be faster. Then for AVL tree, it follows the height balance property. So it tells you that the height of the children should be at most 1. Okay, so the difference of the height of the children should be at most 1. So it could be either left heavy, -1, or right heavy, 1, or balanced, 0. But if it exceeds 1 or -1, then you should do rotations and restructuring to preserve the height balance property. Okay, and then for red-black trees, it's a binary search tree that is colored, the nodes are colored red or black, and then it follows the 3 rules. So the root should be black, there should be no red succession, like so the children of the red node should be black nodes, and then finally the black depths should be equal, so all the root to null paths should have the same black depth. Then if you follow those 3 procedures, then it should be balanced more or less. And then every time you insert or delete, you should do rotations and restructurings and recolorings so that the 3 properties are preserved. So AVL trees and red-black trees are self-balancing trees because they do the necessary adjustments so that it keeps the tree balanced. And then for 2-4 trees, it's a perfectly balanced tree, but it's not binary, so it could have 2 children, 3 children, or 4 children. But if one of the children is missing, then don't have children at all. Okay, so yeah, and we also found out that red-black trees and 2-4 trees are basically equivalent, so they're just the binary tree representation of 2-4 trees. Okay, so that is it for ComSci 123. I hope that you learned a lot with the data structures and the abstract data types that we discussed, and I hope that you can apply this to your future ComSci courses and even later on when you graduate and when you have a job, because data structures are very important in computer science. They're one of the key concepts, right? Together with algorithms, they form the heart of the computer science. And so even when you graduate, the lessons that you learned here will be very useful, and I hope you learned something new. And yeah, so that's it for ComSci 123. Thank you for this semester, and I will see you next time.